Thank you, everyone. I'm with Meter Group, and we make an array of environmental instruments to measure lots of different parameters. And my role with the organization is the product manager for the Teros volumetric water content sensors and the client support manager. So I've looked at a lot of soil moisture data sets with the primary goal of determining if the sensor is meeting its specifications. And then if it is, what else could be happening in this data set? And there are three main factors in soil moisture accuracy for sensors. There's the installation, the calibration, and the sensor performance itself. So I'm going to focus on how to evaluate the sensor performance today. And the main challenge, everyone is familiar with this one, is how do you compare one set of volumetric water content measurements to another? We're using different makes and models, different sensing technologies. There's different relationships between the electrical properties of the soil and the water content. That's the calibration. And the sensor itself has variability from one sensor to the next. So one method we've seen quite a lot here, take gravimetric samples, weigh it, dry it, weigh it again, and get the actual water content measurement. But soils make pretty terrible standards. So a couple other methods is a dielectric standard is one that's been out there for quite a long time. We've heard the term bulk dielectric permittivity a couple times today. So without going into the complex physics behind it, you can look at dielectric permittivity as the soil's ability to store an electric charge. And to make it a little bit simpler, a soil with a high water content is going to have a higher dielectric than a dry soil. And so there are dielectric solutions. This is not a new technique. It's been around for quite a long time, where you've got a solution with a known dielectric permittivity. And with some different ranges, you can cover the entire soil water content range and kind of mimic the soil water content. And since they have a known value, there's just 3 examples here. Dioxane, and the dielectric is 2.2, which comes out to about 1% volumetric water content if you're using the top equation to calculate that. 92% isopropoxy ethanol comes out to about 30% VWC. And then if you want the high end, really high end, you can do something like isopropyl alcohol. And so with a bunch of different mixes, you can hit whatever range you want and remove the variability of the soil. So you're getting a real standard to compare one sensor against another. And one of the most valuable things about this is to compare different soil moisture sensors. And these are 2 meter sensors, the GS3 and the Teros 12. And you can, we have the GS3 dielectric on the x-axis, the Teros 12 dielectric on the y-axis, and they should fall right along the 1-to-1 line. You can see outside of the mineral soil range, something happened. We missed the line by a little bit out there. By then, you're going to be using soilless calibration or something like that. But now we have this comparison between the 2 sensors, which is really difficult to get at without standards. This method does have some limitations, and it's not field portable at all. Some of these chemicals are toxic. They have proper storage, they have a shelf life, they can get contaminated, and then they're a bad standard, which is kind of worse than no standard at all. And you have really limited throughput. It takes a long time to do these analyses for quality control. So one of our solutions for this problem is a simple field clip. And it's a known capacitance. It just clips onto the sensor. You can use it anywhere. And what you get is a range. The sensor either passes or fails. There's no interpreting the data. There's no special technique. The clip only fits on one way. That wasn't a challenge. And On the right, you can see a value. The sensor is right in the middle of the clip range. The sensor is doing what it's supposed to be doing. They're cheap, they don't have any maintenance, and like I said, you can run a lot of sensors through testing on one of these. So what's the first thing you do when you get a new toy like this? You run it on 1,000 sensors. So here we've got 1,500 Teros 12s that we ran the verification clip, 2 verification clips actually, to get a range of, to capture the high water content range in soils, or the mid-range, about 30%, and the lower range of soils, closer to 5 or 10. And most, 95% of the points fall within plus or minus 1% volumetric water content. Now, these are the individual probe data, and on the y-axis, we have the expected minus the observed water content. So the raw data has been converted to water content for these, and we're able to test large populations of sensors this way. And it's not a perfect solution. You can see the difference between the probes in this picture, right? So they don't take into effect the geometry of the sensor. And what that means is that the clip will give you the exact same readings on both of these sensors. But if you stick them in the soil, they'll give you very different readings. So there are very different, there are some limitations to the sensor, or to the clip. It does only work on Teros sensors, and you do have to dig the sensor up at the moment. But in addition to, it doesn't make the gravimetric analysis or the dielectric standards any less necessary, but it's an extra tool in your toolkit to evaluate the sensor probe, or the sensor performance, and it's a lot easier than both of those others, and you can just run a lot more sensors. And that's what I have. I'd like to welcome any questions.
Questions from our audience? I got one. What does the clip do? Is it like a capacitance blocker?
It's literally just a capacitor that
Okay.
you bridge to things, and that's why a short clip will give you the same as a long clip on the clip, as a long needle on the clip, because it basically short circuits the soil as a dielectric. You don't get the full field.
I like it. That paper's a long time ago. Sorry, Scott.
You didn't even have to bring attention to that. I wasn't gonna. Go ahead. A couple more questions.
Hands keep.
Well, I just wonder if the clip is giving us the whole story, because it's going to give you the real part of dielectric, not the imaginary part related to the DC electrical conductivity. And so when you gave us the plot of the 1,500 sensors with the plus or minus 1%, you didn't apply your clip with random amounts of series resistance in there as well, right?
That's exactly right. And this is, that's right. It doesn't give you the imaginary dielectric, but so if you're, especially on the Teros sensors, if you're not meeting the assumptions of the sensor, like your electrical conductivity has to be below a certain range, right? And for that sensor, it's about 10 decisiemens per meter saturation extract DC. So if you're above that, this sensor isn't going to help at all. And it's not going to give you a performance in a condition like that. And that's where the dielectric standards don't really work that great either. And if you've got a lossy system like that, you really need to go to, is this the right probe for the job? Or and then you're measuring the water content under those conditions and developing a custom calibration. So one more.
Any plans to develop the clip into other sensors?
Other Teros sensors for sure. Yeah, we'll have to get back to you on that question.
Anybody else? Good. Okay, let's thank. Oh, Campbell has a question.
Be nice, Todd.
Hey, no, Chris, thank you. Of those 1,500, did you find any that were outside of spec?
No, not in that data set. Those are sensors that passed our production already, so they'd been normalized already. So if they had failed, then we would have had to go back into our population, look at we have procedures for all that. This is a verification, and they are used in production to screen sensors in some cases too.
Okay, Chris, I think you're off the hook.
All right, thank you all.
Thanks.